On March 23, 2012, NASA Mission Control informed the crew of the International Space Station, ISS, via radio that a large number of micrometeoroids were going to collide with the ISS in the next 6 minutes. This radio message caused panic throughout the ISS. The astronauts had so little time that they couldn't even change the direction of the space station. But the question is, the part of space where the ISS is located has countless micrometeoroids, so how does the ISS survive them? Changing the direction of the ISS, which is as heavy as 380 cars, without fuel and without Earth's help. How is this done? How is elixir transported to space? And when the ISS is on the other side of Earth, how is contact maintained with it? Welcome once again to Discover TV's videos, viewers. Built at a cost of $50 billion or 12,375 billion rupees, the ISS is a human home in space unlike anything in history. Hundreds of high-tech parts have been used in its construction so far. It has 16 pressurized modules with separate modules for living, sleeping, and observation deck, and 6 science labs, all connected through airtight tunnels. Additionally, there are many empty spots on the ISS, some for parking extra capsules and some with permanently docked life boards so that in case of an emergency, astronauts can safely return to Earth. The International Space Station is the largest space station ever built. The ISS is as big as a football field and, although it's 400 kilometers above the ground, it can still be seen from Earth with binoculars. To understand its size, imagine the base of the Burj Khalifa. The ISS is even larger. It weighs a total of 460,000 kilograms, equivalent to 380 cars or 25 passenger buses. But the question is, how did such a massive and heavy ISS make it to space? The ISS began with just 2 modules, connected in space, one built by the USA and the other by Russia. After the Soviet Union collapsed in 1992, the USA and Russia collaborated to build the ISS. First, Russia sent a module called Zarya to space, and then the USA launched its Unity module after it. Traveling at 27,000 kilometers per hour, Unity caught up with Zarya, and on November 20, 1998, at 6:40 a.m., the 2 modules connected for 100 kilometers above the Earth, marking the birth. Since then, over 26 years, engineers from all over the world have built and sent their modules into space to connect with the ISS. Today, in addition to US and Russian modules, European and Japanese modules are also attached. Since the year 2000, not a single day has passed in 24 years without astronauts present in the ISS. To meet the needs of the astronauts, the ISS has all the necessary facilities of a superstructure, the most important of which is oxygen. A human can survive for 3 weeks without food, 3 days without water, but only 3 minutes without oxygen.
400 kilometers above the Earth, where there's no atmosphere or breathable air, the biggest challenge for the ISS is providing astronauts with fresh oxygen. An average human needs 15,000 liters, or 20 kilograms of oxygen per day, for 9 astronauts. That's nearly 200 kilograms of oxygen daily. Truly a massive challenge. The ISS keeps several days' worth of oxygen in tanks so that if the system fails, astronauts can survive until the next rocket arrives with a new supply. Today, technology is so advanced that oxygen can be sent from Earth to the ISS in just 6 hours, but only if the rocket launch is successful. This method is good but very costly. A cargo rocket trip to the ISS costs $200 million, or 500 crore rupees. Food and other supplies are sent every few months, but it's nearly impossible to meet the daily 200 kilograms oxygen demand with rockets. That's why the ISS makes its own oxygen. A small machine on board uses water to produce oxygen. When electricity is passed through water, it splits into hydrogen and oxygen. Hydrogen bubbles gather at the positive electrode and oxygen bubbles at the negative. On Earth, these bubbles separate naturally because gases are lighter than water, but in space, there's no gravity. Both water and gas weigh the same, practically zero. To separate oxygen gas from water, the machine is spun, creating centrifugal force and artificial gravity. Spinning pushes water to the sides, leaving oxygen in the center, which the machine collects and stores. Now you might wonder, If the ISS makes oxygen from water, where does the water come from? Here too, great engineering comes into play. The hydrogen gas produced in the process is reacted with carbon dioxide exhaled by astronauts to create water again. The final byproduct is methane, which is discarded into space. Making oxygen is a huge challenge for the ISS, but an even bigger challenge is preserving it. A small leak in the ISS could have disastrous consequences. The entire station could explode in a second. A recent example is the Titan submersible disaster. In the ocean, external pressure is high, and when Titan's hull leaked, the ocean pressure crushed it in less than a second. Space is the opposite. Zero pressure outside, and maintain pressure inside the ISS. If a small crack appears, it can depressurize and explode. Just like Titan, the ISS orbits Earth at a height where space debris is abundant, moving at high speeds. This includes satellite parts and hundreds of micrometeoroids. So how does the ISS protect itself from these? The ISS travels at 27,000 kilometers per hour, fast enough to cross the Pacific Ocean in just 25 minutes, whereas commercial planes take 13 hours. At such speed, even a grain-sized meteoroid can hit with the force of a car crashing at 80 kilometers per hour.
On March 23, 2012, NASA Mission Control radioed the ISS crew that some space debris was heading directly toward the station. No one knew how big it was. They were only warned 6 minutes earlier. The entire crew rushed into the lifeboats. Fortunately, the debris passed very close to the ISS without hitting it. But we can't rely on luck every time. To withstand small particles, the ISS is made with bulletproof materials. Like bulletproof vests have multiple layers, so does the ISS hull. The outermost layer is aluminum, followed by a woven material, and then another aluminum layer made of bare. A single metal isn't strong enough, but multiple layers of the same metal are. Every moment, the ISS is bombarded by micrometeoroids, but these bulletproof layers have protected it for 26 years. However, if a larger meteoroid, even just 1 inch in size, hits the ISS at such high speed, the bulletproofing won't help. Mission Control on Earth already tracks potential meteoroids that might pose a threat. If danger is imminent, the ISS's trajectory must be changed. Small thrusters on the ISS can be used for this, but they run on rocket fuel, which is limited and only for emergencies. To reduce Earth dependency, the ISS uses a mechanism to change its direction without rocket fuel. At the center of the ISS are small boxes called Control Moment Gyroscope (CMG). How do they change the direction of a space station the size of a football field? Inside these boxes are fly wheels that spin at 6,600 revolutions per minute. These heavy wheels, like train wheels, create angular momentum when spun at high speed. This momentum is transferred throughout the ISS body, causing it to move in a direction. If the flywheel spins faster, the ISS turns more. If the direction needs to be reversed, the flywheel is spun in the opposite direction. These flywheels are powered by electricity generated by the ISS's solar panels. Speaking of solar panels, they are movable. Since the ISS orbits Earth so fast, the sun rises 16 times a day. The sun shifts position so rapidly that fixed panels wouldn't get direct sunlight and couldn't generate proper electricity. That's why the panels always face the sun. ISS's solar panels can generate 120 kilowatts of electricity at a time, enough to run 110 air conditioners on Earth. Maintaining communication with the astronauts was once a major challenge for Mission Control. Communication happens via radio signals, which can't pass through Earth. Often the ISS is on the far side of Earth, causing disconnection for an hour until it comes back in range. Previously, planes were flown to catch radio signals from the ISS and transmit them to Houston Mission Control. This was costly and unreliable.